This podcast is involved with enthalpy, specifically Hess's law and enthalpies of formation. What's enthalpy? Well, enthalpy is heat. And heat is the energy change plus any PV work that is done on the system. Rearranging, the change in energy is the change in enthalpy minus the work done by the system on the surroundings. Well, if the pressure is constant, we can rearrange this to say that delta H equals delta E plus P delta V, and then since delta V is 0, we're adding 0 to delta E, and delta H is equal to the energy flow as heat. And constant pressure is what we are commonly at in the chemistry lab on the benchtop. The change in heat content of a system that accompanies a process at constant pressure is known as the enthalpy change, or delta H. That's a definition that you need to be very, very aware of. And we use them in thermochemical equations. These are equations that contain the information about how much heat is gained or lost in a reaction. In the top one, the methane is burning. It is releasing 890 kilojoules of heat there on the product side. If we write it in delta H notation, it becomes negative 890 kilojoules. If the reaction occurred in the opposite direction, then the 880.3 kilojoules ends up on the reactant side, and the delta H becomes a positive value. So, the coefficients that are there refer to the number of moles of reactants and products involved in the balanced equation, to which the delta H that is given applies. The delta H is usually written in kilojoules per mole, but it does apply to the reaction as written. It's directly proportional to how much reacts or how much is produced. And you may have already done calculations like that in a previous chem course. Remember, the sign of delta H for an exothermic reaction is negative, and that's because the stored energy is decreased. The energy of the system goes down. That means the energy of the surroundings goes up, which is usually accompanied by a temperature rise. Look at the combustion of methane. Here, the system is composed of reactants and products, and that delta PE for a mole of methane reacting is in fact the difference of 890 kilojoules. And that energy is released to the surroundings as heat, and that's why we use methane as the burner in the lab. For an endothermic reaction, it's reverse. Delta H is positive. The stored energy is increased. The energy of the system goes up. That means the energy of the surroundings went down, so the temperature of the surroundings will decrease. If you look at the reaction of nitrogen and oxygen to form nitric oxide, calculations show that the products have much more energy than the reactants, so the heat is absorbed from the surroundings as this reaction occurs. This is an endothermic reaction. Sample calculation, like we said. Here you have the combustion of glucose. We burn 9 grams of glucose at 25 degrees C. The equation has 2,820 kilojoules released for every mole of glucose that burns. 9 grams is a small fraction, and the answer is 141 kilojoules, and it is negative because it is released. Standard molar enthalpies of formation are the amount of heat absorbed or evolved when 1 mole of a substance in its standard state is formed from its elements in standard state. Molar enthalpies of formation are critical to an understanding and the ability to work with heat problems. Standard states, what do we mean? For a compound that's a gas, it's a pressure of exactly 1 atmosphere. For a solution, we've defined it as exactly 1 molar. And if it's a liquid or a solid, it is the pure liquid or solid with no impurities. For an element, it's the element in the form in which it exists at 1 atmosphere pressure and 25 degrees C. So in thermodynamics, standard temperature is 25. Unfortunately, the gas chemists decided to use 0. Here, it's 25 degrees C. Example. A 1 gram sample of sodium is burned in excess chlorine gas and 1 atmosphere pressure, and we get this much heat. First of all, we would like to write the reaction for this, and this is the standard heat of formation reaction for sodium chloride. Well, Na solid plus a half chlorine gas makes an NaCl solid. Sodium is normally a solid at room temp. Chlorine is a gas, and table salt is clearly that white little solid. Then, calculate the standard molar heat of formation. Well, you take the value that you have and divide it by the number of moles that we've got, and we get an answer of negative 162 kilojoules per mole, which is reported as the delta H of formation of sodium chloride. What about the standard heat of formation of ethanol? What would that reaction look like? Well, you have 2 carbons in their solid state, 3 hydrogens in their gaseous state, plus a half an O2 in its gaseous state, to make 1 C2H5OH, which is the ethanol, which is a liquid in its natural state. That's what it would look like. Hess's law. Hess's law is relating reactants and products. It states that the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. It's path independent. Look at the process to produce NO2. It could be a 2-step reaction. It could be a 1-step reaction. Kineticists have worked on this and believe they know what the answer is, but from a thermodynamicist point of view, it doesn't matter. The delta H is always 68 kilojoules. Notice that if it's in 1 step, it's 68 kilojoules. If it's in 2 steps, a lot of heat goes in, a little bit comes out, and you still end up with a net difference of 68. That's the principle of Hess's law. Path is unimportant. Look at methane. Methane can do a variety of things when it burns. This graphic is from your textbook. Okay? The methane has to break apart into carbon and hydrogen, the oxygen possibly into itself or nothing, and then you end up producing the products. If you look at it at a particle level, here's the steps, and we get the rearrangements, and we have energy changes, but still, in the end, the energy change is the 890.3 kilojoules per mole, released or negative. We can do calculations with Hess's law. One of the things you have to remember is that if you need to write a reaction reverse, delta H is reversed. N2 plus O2 makes 2NO. Delta H is 180 kilojoules. Okay? If we were to write it in the opposite direction, it's negative 180. If the coefficients of the reactions are multiplied by an integer, you have to multiply delta H by that same integer. So if we had 6 NOs involved, it's now negative 540 kilojoules. So, calculate the standard enthalpy of formation of SO3 by proper combination of the following reactions and enthalpies. But what you'll notice is we've got a standard enthalpy of formation and we've got a combustion reaction. Now the answer to this is pretty straightforward. We have the sulfur producing the sulfur dioxide, and we also have 2 SO2 making 2 SO3s. But we don't want 2 SO3s, so we write that reaction by dividing it in half. And you notice that the heat value is cut in half. And then you'll see that the SO2s cancel, and you end up with a final reaction of S plus 3 halves, or 1.5 O2s, produces the SO3. And the delta H for this reaction is negative 396 kilojoules. Now try this one. What you should do is stop the podcast and work with this. Here we have the delta H's for a variety of reactions. Let's work it together. Hopefully you got 13 kilojoules as well. The mathematical statement of Hess's law is that you can calculate the enthalpies of formation of the reactants and the products and use them to get the answer. That is, delta H reaction equals capital sigma, the sum of the molar heats of formation of the products times the number of moles of products minus the sum of the molar heats of formation of reactants times the moles of reactants. So it is the difference of we're at the finish and we subtract where the start was, which is what we do in real life. So here's an example. We're going to burn some ethylene to produce carbon dioxide and liquid water. Now what we need to do is calculate the delta H of combustion for this reaction given those standard molar enthalpies of formation. Those are all in kilojoules per mole. The product is delta H equals the sum of the delta H of the products minus the reactants. And we put in the values. 2 times negative 393.5 plus the 285.8 for the water minus the 49.03 for the C2H4. We get an answer of negative 1,408 kilojoules. And that is indeed the value. Now try this one. What you need to do is stop the podcast and work this one through using the exact same method, except what we're looking for is one of the heats of formation because we already know the heat of combustion. Assuming you did so, your answer is going to look like this. You have the reaction up above. Products minus reactants gives you the delta H. Well, we know the delta H is negative 3268.5, so it equals 6 times the carbon dioxide value plus 3 times the water value minus our unknown, which is the heat of formation of the benzene, which is 50.1 kilojoules.